session. On the web panel, you can actually see there's a chat box, and people will basically post questions on the chat box. So we'll have 10-15 minutes, and whatever best we can address, we can try to address. But you need to again press the *71.
So
sorry.
Just a variation I want to propose is that I typically want my presentations to be interactive. So do you mind if I don't do *71 and allow people to ask questions during the talk? And is that?
I'm fine with that. My only concern with that is since we expect anywhere close to 100 plus participants joining in, if there is disturbance in the line and if moderating them becomes a problem, then others may get disturbed. That is my only concern, but I'll leave it to you. If you want to route it that way, I'm fine with that. But just be aware that if somebody is on mobile or somebody's at home and there are dogs barking and kids crying, all those things may pitch in.
Okay, that makes sense, right? So I'll probably do what you suggest, *71, and then probably open it up for questions at the end.
Yeah, you need to press the *71 again. When you open it up, you need to press the *71 again.
Okay. So let me just recap this. 5 minutes, I do *71, and then towards the end, again, after 40 minutes, I do a *71. Okay, got it.
Yeah, that's right. So you can start off with a brief
mostly,
introduction about yourself.
I am oriented people, right? So I won't probably go too much into system details, but generally give a broad overview and stay on the motivating side of things rather than anything else.
Yeah, that's right. That's absolutely right. And the audience is primarily from the technical community, from system integrators, TCS, Infosys, and the likes. So,
okay. Got it. Okay. So it's 10:15 here, so 15 minutes.
You can actually go ahead with the *71 right off. You can go ahead with that. And when you start the Q&A, you can open the line.
Yeah,
and
so
we have
ping me when you're ready to start.
Yeah, I'll ping you when we're ready to start, and you can just right now basically put the line on listen-only mode.
Sure. Okay.
Yeah.
All participants are now in listen-only mode. All participants are now in interactive talk mode. All participants are now in listen-only mode.
Hello. My name is Prasenjit Sarkar. I'm a researcher here at IBM in the USA. So I've been at IBM for about 15 years, and I have done a lot of projects with in various facets of technology. And what I'm going to cover today is the GPFS FPO file system that is built towards big data, and in particular is used with big insights. So I'd like this talk to be interactive. I realize that there are a lot of people who may want to ask questions in between. So currently the teleconference is not interactive, but what you can potentially do is that you can ask questions on the web conference, and I'll be happy to answer them as I see them. So hopefully, with this arrangement, I should be able to stop and look for questions and answer them as I go along. Sometimes contextual questions are more interesting, so I would like to encourage that. So without further ado, let me just start on the basic motivation behind my presentation. So what I show out here is a chart from IDC in this page, which shows the amount of information that is being created. And as you can see, the y-axis is actually petabytes, and it was forecast, and actually the forecast was actually exceeded in that by 2011, IDC predicted that there would be 1.7 exabytes of data, and in reality, we actually exceeded that. The number is not exactly known, but the estimates are around 2 to 3 exabytes of data. So the question is, what do we do with so much data? And the answer is actually we want to provide decisions in very quick time. So the most famous example, and I've used this in a lot of talks, is that whenever you go to a bank and say you talk to a customer rep or a portfolio manager, typically what happens is that the portfolio manager says, hey, let me look at your assets, let me look at all your bank accounts, and let me give you an investment strategy in a day or two. But today the world has changed, and people expect personalized recommendations right there and right now, which is sort of called the right now economy. And in that economy, what people expect is that if you go to a portfolio manager with all your assets, you expect an answer regarding your, say, investment decisions right there and right there. So the advantage is that you have the customer locked in. So if you lose the customer for a day or two, he might meet some other person and invest in some other vehicle. So as soon as you have the customer locked in, you provide them a recommendation, and the customer does the investment again right there. So what essentially this means is that you have a large amount of data to process, and you have not a whole lot of time to actually deliver results. And so this is the premise for big data, where you are likely to process a huge volume of information in a fairly short order of time. And so consequently, what we are trying to achieve out here is to provide a framework by which you can achieve that particular goal. So I'm moving on to slide 2. So we examined our assets in IBM, and one of the things that we were focusing on is whether the existing infrastructure is good enough for such kind of decision making. So in particular, we looked at the traditional way storage is configured, and that is using storage area networks. And we found that the structure was meant more for online transaction processing. So this is more like your bank transactions. And so what you end up doing is the fact that you build it for latency. So you want a very quick response time for a transaction, but it's not built for processing large amounts of data in a short order. So for that, what has been proposed and implemented in various companies around the world, such as Google and Facebook and Microsoft and Yahoo, is the concept of a shared nothing environment, where the idea is to get scalable bandwidth. Now, the utility of scalable bandwidth is that it allows you to process a large amount of data in a short order of time. So, for example, if you are able to get, say, a gigabyte per second out of a single server, the premise of the shared nothing architecture is that with 100 servers, you can get 100 gigabytes per second. And so if you keep adding the number of servers, then potentially you can scale the architecture to the bandwidth requirements of your application. So, for example, in a recent customer environment, we had to process somewhere on the order of 800,000 trades in a matter of 5 hours. And the only way we could do that is by scaling the architecture to the needs of the application. So we calculated the amount of bandwidth that would be required, and we calculated the amount of CPU processing that will be required to do the analysis of the 800,000 trades, and we proposed a shared nothing architecture to solve the problem. So now that we know that we need a shared nothing architecture, so what base do we start to build on? So in IBM, we already had an enterprise file system called GPFS. It already has the high scale. It scales to thousands of nodes. And recently in a supercomputer in Germany, it scaled to about 10,000 nodes. And there is a proposal to scale it to as high as 50,000 nodes in the future. So with such a scalable file system in our hand, which supports various advanced features like, say, workload isolation, where you can isolate one workload from another workload. It has things like security, such as encryption, snapshots, backup restore, archive, as well as asynchronous caching and replication. So since it has all those features, we decided, why don't we start here and then add the features that are necessary for adapting it to this new shared nothing environment. And so as a marriage of two, the GPFS, the traditional GPFS, and the demands of the shared nothing architecture, we created this file system called GPFS SPO. So any questions via the, the web, you can raise your hand and ask questions, but if there are none, I'll move on to slide 3. So this is sort of a marketing slide for GPFS. So what this tells us is the fact that GPFS is used in a wide variety of applications. And so things like Oracle and DB2 run on GPFS. So if you've heard of the scale-out NAS product that also runs on GPFS, it's used a lot in the supercomputing area in Perks and Blue Gene. So essentially what this means is that since a wide variety of applications use it, it has a lot of configuration parameters to adapt it to various kinds of applications. And we have found this particularly useful in the kinds of environments that we see in big data, not all of which are MapReduce related. So when we run into other non-MapReduce applications that also process big data, we found that the experience from all these prior customer usage helps a lot. Okay, so that was the marketing slide about GPFS. So I'll probably move on to the next slide, which is slide 4. Um, this slide is a sort of a brief overview of the rest of the talk. It describes the architecture of GPFS in greater detail. Um, so uh, the first thing to note is that this is a shared nothing architecture. So every node owns its own storage. So, for example, node 1 has its own storage. The storage could be solid-state disk. It could be locally attached SATA drives. It could be SAS drives. You could even attach a fan behind it, but make it appear like local storage. But in the key differentiator between, say, a traditional GPFS and this model is that every node owns its own storage. So now that we have laid out GPFS on top of this architecture, so I want to point out the differentiating features. So one is the fact that we don't have any single point of failure. So every service in GPFS is both distributed and replicated. By distributed, it means that there are many copies of the same service which can act in parallel. So, for example, if you want to operate on many files in parallel, the distribution helps you a lot. Similarly, the replication helps with fault tolerance and high availability. So, for example, if any node or any set of nodes goes down, then using the replication feature, you are able to survive the failure and still be up and running. So the twin properties of replication and as well as distribution allows us to have a very resilient parallel file system. So in addition to having no single point of failure, we have added in many distinguishing features which are not there in competing file systems. So the first is the support for multiple block sizes. So GPFS is a file system that allows you to specify multiple block sizes within the same file system. So how that helps us is the fact that if you have different kinds of applications, and this is something that we have seen even within, say, Hadoop applications, that some applications like large block sizes and some applications like small block sizes. So if you're doing sequential scans, you will want to have large block sizes because you will want to do a lot of prefetching and grab the data as fast as you can. But then when you have things like index lookups, you want smaller block sizes because you're essentially doing random I/O operations. So in effect, what we have provided is a tool by which you can specify a different block size for every file in the file system or for all the files in a directory, so you can make it a property of a directory, and or alternatively, you can also specify a default block size for the file system as well. So that's one key distinguishing feature of our file system. The second distinguishing feature is the ability to control data layout. So what we have provided is that we allow applications to control the layout of the data to the maximum extent possible. And this allows us to make sure that the layout of the data matches the needs of the application. So we will go through some examples later on. So one example I will give is a traditional Hadoop where you write one copy of data locally and then stripe the rest over multiple nodes. But then there are other things like databases which want different layouts. And the ability for applications to dictate the layout of the data is an important differentiator in our file system. The other aspect is that we also provide smart client-side caching, so repeated accesses to the same data don't go out over a network. So we feel that with the support for both POSIX as well as MapReduce with features such as disaster recovery and scale and tiering, as well as the support for storage pools, and the differentiating features that I just described, we should be able to provide a very highly differentiated file system for big data. Any questions? You can raise the hand and ask questions. Otherwise, I will move on to the next slide. So one of the features that we have built into our file system is that we provide interfaces by which we make the application completely transparent to the fact that it's running on top of GPFS. So in the case of the Big Data Hadoop world, we subscribe to the DFS API. And so in particular, we provide a connector which provides the DFS API to the applications. So in addition to the standards, read, write, and other features that are required by applications to operate with the file system, we also provide the block location information. And the block location information is used by the Hadoop scheduler to schedule tasks on nodes where data is running. So one of the important properties of Hadoop is the fact that it ships compute to where the data is rather than the other way around. And what we have shown in this is the fact that if you marry, say, GPFS and expose the block location information to the Hadoop scheduler, it works just as it does with HDFS. And so, consequently, we allow for locality awareness and are transparent to the universe of Hadoop applications. So if there are no questions raised over the web session, I will go on to my next slide. So the thing that I mentioned out here was that we, in the couple of slides back, was the fact that we allow applications to define their own logical block sizes. So as I mentioned before, small blocks are good for index file lookups, whereas large blocks are good for sequential scans. So we allow for multiple blocks in the same file system. And what the application provider does is that he specifies something called a block group factor. And we take the physical block size of the file system and multiply that by the block group factor to get the effective block size for a particular file. And as I mentioned before, you can do it for a directory so that you can cover a lot of files within the same directory, or you can specify a default for the file system. And the block group factor is used by the file system to determine the logical block size, and that's what the application actually sees. So the question that comes from a lot of implementers is, how do you determine what is the right block group factor for a particular file or a particular application that is accessing a file? And there is no hard and fast rule. This is something that you determine empirically. So if your block group factor is too low for a particular application, then your performance will get affected because you are not delivering enough data to the application. On the other hand, if your block group factor is too high, then it sort of makes the overall strategy too greedy, and becoming too greedy also hurts performance. So what we have found out is that the optimal performance happens at a certain point. And I won't go into the details of this graphs out here, but as I mentioned, you have to run your own experiments to find the optimal block group factor. So for Hadoop applications, we typically run with 128 or 256 with a 1 megabyte block size. And that has performed reasonably well for the configurations that we have tested so far. So after this, I'm moving on to the next slide. So the other feature that I mentioned in the opening slide in the architecture is the fact that we allow applications to dictate layout. So traditionally in GPFS, what happens is that you don't have layout control, and all files are striped over all the disks in the file system. So this is something that takes away the freedom of the application to dictate its own layout. So what we have done is that we have provided knobs to the application to say how the files should be laid out. So in a typical shared nothing cluster, you use a replication factor of 3, which means that there are 3 copies of data in the file system. So as a result, what happens is that what we allow is the fact that each replica can be laid out in a different way. So what are the different ways by which replicas can be laid out? So one is called write affinity, where you can say that this file resides on this node and in this set of disks. So that's where you sort of give the affinity of a file to a particular node or a set of disks. So in this particular example, you can say that file 1 is entirely contained with node N1, and that is a form of write affinity. On the other hand, if you say that file 1 is striped over all the nodes N1, N2, N3, and N4, it means that particular file is white striped. So what we allow in GPFS is that we allow the user to specify both white striping as well as write affinity. Write affinity is good for making sure that you get the optimal read bandwidth. So if you read file 1 from node N1, you get the maximum bandwidth and you're able to read it very fast instead of sending a request over the network. The second thing that we want to do is to have quick recovery. So if we allow a file to be white striped, and then if we have a failure, then all the nodes recover in parallel. So you get bits and pieces of the data from different nodes in parallel, and so you're able to recover faster. So write affinity has an advantage with respect to bandwidth. White striping has an advantage with respect to recovery. So what we have done is that we have allowed applications to decide what combination they want. So one combination is, and this is what is used in HDFS, and you can also specify that for GPFS as well, is that you can allow your first replica to be have write affinity to the writer node, and the second and third replicas are white striped. So GPFS does allow this feature, but GPFS goes beyond that. So it allows you to decide which replicas are white striped and which replicas have write affinity. So in databases, what we do is that we have write affinity for, say, 2 copies, and a third copy is white striped. So what that means is the fact that if you have a table on one node, and suppose that node fails, then you can quickly fail over to another node and have a table in another node as well. So what this means is that different applications are able to tailor the write affinity or white striping depending on the requirements. We have worked with other applications beyond big data where we have tweaked it to provide synchronous disaster recovery. And this is all done using write affinity, by which we are able to place the primary copy on one site and the secondary copy on a disaster recovery site. So write affinity allows you for applications to dictate layout, and at the same time, it also allows for good performance as well as faster recovery and even disaster recovery. So moving on to the next slide, I'm going to skip this particular slide, but what we do is that in GPFS, we treat data, file system data, and file system metadata differently, and we use this by using a concept called storage pools. And what this allows us to do is to provide both high availability as well as good performance. In the interest of time, so since we are already reaching approximately the half-hour mark, I will probably skip this slide, and I will go to the chat section and answer the question. Okay, so the question from Mr. Ghosh, who's on the phone, is that in HDFS, metadata is stored on the name node. And as part of GPFS, the question is this metadata replicated across each of the nodes? And the second question is, if it is replicated across each of the nodes, will it not be a big overhead in GPFS? So let me answer both these questions one by one. So the first question, again, was, is metadata replicated across all the nodes? So, so if you look at HDFS, all the metadata is stored in memory, and the memory is, say, on the order of, say, 128 gigs or thereabouts. So the total amount of metadata is not significantly high. 128 gigs is not a lot if you look at today's disk sizes, which are, say, 4 terabytes each. So even if I take this 128 gigabytes and replicate it 3 times on disk, it's going to take, say, about 384 gigabytes. And in general, what we've found is that even for very highly populated file systems, so let's say we have a petascale file system, the amount of overhead is, say, on the order of, say, 1 to 2%. And that's the metadata overhead of the file system. And so what we tend to do is that we reserve 5 to 10% of the disk space for metadata, and the remaining is for data. And that is sufficient enough for the metadata requirements of the file system, even though it may be triply replicated. In terms of processing, this metadata is also cached, and since the metadata for frequent usage is mostly in memory, we do not find a significant difference in processing times between, say, HDFS and GPFS. In HDFS, it's stored in one node. It's going to go to multiple nodes in the future, but in GPFS, it's already stored in multiple nodes, and we are able to exploit the parallelism inherent in the distribution. So I hope that answers this question. But so in general, GPFS has a different, historical path than HDFS. And what we are trying to do is sort of use GPFS in its own way to mimic the metadata requirements of the name node. So with that, I think what we are trying to say out here in this particular slide is the fact that we treat metadata and data differently. We proportion a section of the disk for metadata, so typically it is 1 per rack, or we have about, say, 3 or 4 metadata disks per rack, and so that's sufficient enough for most Hadoop applications. So with that, moving on. So one of the things that we also support is pipeline replication. So with pipeline replication, what the main motivation is, it uses bandwidth more effectively. So pipeline replication can be defined by way by which the replication occurs in a series. So if you look at the picture on the bottom, so if suppose the client writes a block P, and it wants to write to nodes N1, N2, and N3, what we do is that we form a pipeline, a write pipeline. So when the client starts writing block B and copy 0 to node N1, N1 immediately starts replicating the data to node N2, and that's the block B copy 1. And when N2 receives any data, it starts replicating to node N3, which is block B copy 2. So the advantage of pipeline replication is the fact that it allows you to utilize bandwidth more effectively. So what we have seen is the fact that pipeline replication is good for bandwidth, but there are applications where which are more latency sensitive. So an example of that is HBase. And so in HBase, when you have a lot of small writes to the say to the HBase log file, you want to optimize for latency. So in GPFS, we also have another form of replication called star replication, where a client writes to N1, it writes to N2 as well as N3. And in that case, the writes happen in parallel instead of in a pipeline. So GPFS is different from HDFS in that it allows both what we call a star replication as well as pipeline replication. So you can choose star replication if you want to optimize for latency, and you use pipeline replication if you want to optimize for bandwidth. So in some ways, GPFS does provide you the best of both worlds. So moving on to the next slide. So GPFS also provides you quick recovery from disk failures. So every node in GPFS maintains a transaction log, and this transaction log is very useful in recovering quickly from a failure. So a lot of people, like hopefully in this call, are assuming with transaction logging and other IAM situations, such as say databases and the like. And the file system transaction log is similar to the database transaction log in that in the case of failure, it allows you to replay operations and get back to a crash consistent state. So before I go there, I have a question from the previous slide. So I will quickly go back to the previous slide and answer this question. So I'll come back to this slide in a moment. So I think the question is, when is the write considered complete? So in the case of both pipeline and star replication, so is the write considered complete when N1 acknowledges the write back to the client, or is the write considered complete when N3 or last node in the pipeline acknowledges the write? So what we are trying to do out here is that we do not want to compromise performance for consistency too much. So what in general in GPFS, what we do is that we wait for the acknowledgement from N3 to come back before we consider the write complete. And the reason is simply this, that we do not, if suppose nodes N2 or even N3 go down, we do not want to be in a state where we are not able to recover completely from failure. So we mark, so it's sort of a synchronous write where we mark a write complete only when all the nodes have acknowledged the write. So while this causes a slight loss in performance, we sort of take that hit because it makes the recovery a lot easier. And this is identical for both pipeline replication as well as for star replication. So in the future, we are looking at what is referred to as, I guess the various terms for it, but one way to describe it is for asynchronous replication, by which, say, a client can write to node N1, and when N1 acknowledges back, you can consider the write complete, and then the write can proceed to N2 and N3. However, I think what we need to do there is to make sure that we have logged enough information such that in the case of failure, we are able to recover faster. So this is something that we are working on, and we should be, I think we are prototyping it as we speak. So this will result in good performance for a certain class of applications, but not in general.
नहीं पढ़े तहकीक किया है मालूम है अमेरिका के सांसद ज़्यादा चर्बी नहीं खाना चाहिए.
So the person who is talking, can you please go on mute?
अरे उससे मालूम है कमजोरी. आजकल ही के पेपर में तो पढ़े थे. हेलो, अरे उससे बात कर रहा हूँ, उसका दूसरा वाला पे लगा रहे. लगा.
All participants are now in interactive talk mode. All participants are now in listen-only mode.
Okay, I've put listen-only mode on. Hopefully the disturbance has gone away. So there's one more question, is that when a node goes down, how the blocks on the node are going to fulfill the replication factor? So I think this brings us to the recovery part, and that's the part I'm going to cover on, which is that what happens during failure. And suppose you want to write 3 copies of a data and one node goes down. How are you going to recover from that fact, right? So recovery is an interesting topic. It is one of the most challenging parts of designing a file system. The traditional read-write paths are probably easier. It's mostly logical, but recovery is always hard. And this is something that is true for both database recovery as well as for general recovery. So let me address that. Hold on. So let me not go through this chart in order, but let me address the recovery part. So is there trouble hearing the audio? Okay. So somebody did comment about that. Okay, fine, perfect. Thank you. Let me go back to the slides. So let me explain how the log-based recovery works. So I can use the example on the picture on the top right. So suppose you have nodes N1, N2, and N3, and you have 3 blocks of data on each of the nodes. So suppose node N2 goes down, and so then you still need your file system to be operational at the point, because you still have 2 replicas left. So another client wants to write, and so it writes blocks to node N1 and N3. And as you can see, the write to N2 doesn't happen because N2 is down. So the question is, how do we recover from this state? So when N2, let's say N2 was rebooted and it came back up, it compared its transaction log to the transaction logs of N1 and N3. And what it found out was that once it compares its logs, it will figure out it's missing an update. And then that update gets replayed on N2, and N2 becomes synchronized with N1 and N3. So in GPFS, we have a command called to start a disk. What starting a disk does, it does a transaction log recovery for that particular disk, and it makes sure the disk is up to date with respect to all its replicas. Now, it might happen that your node N2 was down for a significant fraction of time. And so if you're aware of the concept of log rollover, the logs have rolled over and there are no logs from which you can recover from. So GPFS also handles this case, and what it does, it goes to N1 and N3, and it will do a comparison of all files, and if it detects missing update on any one of those replicas, it will fix it. So there are two ways of recovery. One is by using the transaction log. The other way is that we store some metadata which indicates that update was missed, and then we sort of recover from that. There are other ways of recovery also, using a more expensive file system check. But in general, we are able to recover from replication failures. The other thing that we have done is that we have parallelized recovery. I alluded to that a few slides back. But an important part is that GPFS has a very advanced policy engine by which it allows you to determine how you react to failure. So there are two types of ways of managing failure. One is called fail in place, where if something fails, if you want to cut down on maintenance costs, you let the fail node be as it is. And what you want to do at that point in time is to take the data from the fail node and sort of restripe it over all the remaining nodes. So that's one way of dealing with it. The second way is that if it's mission critical, you replace a node right there and then, and you recover the contents of that particular node. So what we have done is that we have provided automated recovery scripts that will, depending on the way you want to handle it, either deferred maintenance or quick replacement, take the appropriate action. So we have a policy-based recovery mechanism inside of GPFS. So I think I've crossed the 40-minute mark, and I'm supposed to sort of wrap up at this point. So I won't. I'll quickly touch upon some of the other things, and so I won't go into too much detail. So one is that. So the first thing is the fact that GPFS supports snapshots. Snapshots are a very useful tool for recovering from operational errors, which are 95% of the errors that you see in a data center. So, for example, you might accidentally delete a file. It's also useful for disaster recovery because you don't want to propagate errors across sites. So you want to get to a good state and be able to propagate that good state onto a disaster recovery site. The snapshots in GPFS are accessible from system root directory as well. So if you want to access a snapshot, you can sort of navigate the file system and access a snapshot as well. Going on to the next slide. So GPFS also supports caching and disaster recovery. The important thing about the disaster recovery in GPFS as compared to the competition is three. So I'll mention the 3 points. The first is the fact that the only deltas are transmitted. So if you modify a very large file, say you have a 1 terabyte file and you modify 1 byte, only deltas are propagated across to a disaster recovery site. The second thing is that the disaster recovery also proceeds in parallel. So you can have multiple gateway nodes that are able to participate in disaster recovery. So all disaster recovery actions proceed in parallel. And the third point is the fact that you can do bidirectional disaster recovery. So disaster recovery, the unit of disaster recovery is directories. So what you can do is that you can have active disaster recovery by which both sides can have directories which are mirrored onto the other side. And so this allows you to have very sophisticated configurations by which you have a certain set of applications on one side and a different set of applications on another side, and both of them can fail over to each other. And this is something that we have made operational in a customer very recently. and the customer has 2 data centers in 2 states in the United States, and we are able to perform bidirectional disaster recovery across these 2 sites. So this is something that is a key leading differentiator, where we are able to provide delta disaster recovery, parallel disaster recovery, as well as bidirectional disaster recovery. So I think I have less than a minute left. So GPFS also provides storage pools by which you can group the same kind of disk together, and it allows for policies which can move data between the pools. So GPFS provides features like retention and immutability, which are very useful for many banking applications or many security and financial applications which need to conform to a certain set of laws. So the big advantage in information lifecycle is the encryption, retention, immutability, storage pool, steering. So these are features that will allow you to manage GPFS within an enterprise. So I have a chart on a comparison with HDFS and MapR. I don't think I have the time to go through this. You can read it at your own convenience. And finally, a roadmap about GPFS in SPO in general. So with that, I'm going to open up this conference to questions, and we have about 4 to 5 minutes left, after which we will probably end the discussion. So thank you, and I'm opening this up for questions.
All participants are now in interactive talk mode.
So hi, the session is open for questions right now.
Hi, I'm Ravi here.
Hello, Ravi. Go on.
Yeah, I had a question here. For suppose the read operation in my HDFS system, it will happen that whenever the client request comes, then it will refer the name node, and the name node gives the client regarding the block information, where exactly the blocks related to that files are located and which data node. But wherever in GPFS, each rack will have a metadata information. So the client directly interact with which data node which will have the metadata information. Why? Because at multiple places the metadata information will be there, right?
Yes, so the metadata information will be there on disks and for a certain set of nodes, but it can be cached in the memory of all nodes. So you just have to query for the block location information on your node where you are requesting that information, or where the client is located, and it will get the block location information on that node. So that's completely transparent, and I think you don't have to worry about where the metadata is located or where the metadata nodes are. So clients do not have to worry about any configuration issues. So it's completely taken care of under the covers.
Okay.
So a couple of questions on the chat session. So when deploying an application on Big Insights, is there any particular node to which it is deployed? If so, would the application be able to access the local file system of only that node? So I think Big Insights applications are deployed on all nodes. So if you deploy an application such as HBase or Hive, these are distributed applications and they are deployed on all nodes. And because these applications are distributed, you would like to have a cluster file system underneath that node. answered that question. And the second thing is does GPFS have an OpenMP interface? Yes, that is correct. It does have an OpenMP interface. It has had it for a long time. Another question was, in HDFS, write is blocking. Only one write can be active at any given point in time. Now, GPFS writes can happen in parallel. That's because we don't have a central point of control, like a single name node. And so writes do happen in parallel and to multiple files in parallel. In addition, you can also write to the same file in parallel as well. So GPFS provides byte range locks, which allows multiple clients to write to the same file at the same time. So I think I answered all the questions on the chat session, and so that's one on the phone. So Bharat, do you think
Yep.
we should terminate this at this point, and then maybe?
Yes, proceed.
And I have my email address with Bharat, and so if there any more subsequent questions, you can always send it by email via Bharat too.
Yeah,
Hello.
that's right, Prasanjit. And is there a question? Okay. Yeah. So, Prasanjit, thanks for the informative session. And just to the audience again, please ensure to answer the online poll on your screens. And also, just a note on the upcoming session today at 3 p.m. IST, we will have a session around the data warehouse appliance, pure data analytics. So do leverage the session. Yeah.
ये समझ पा रहे हैं देखिए फिर सब बात कर रहे हैं.
Okay. So, Prasanjit, I think there's one last question on the chat. If you want to quickly answer that, and we'll wind up this session.
Hello.
Hello. Yeah.
Go on, please.
Yeah. May I know who's speaking?
This is Prasanjit, the presenter.
Okay. Actually, sorry. I guess we were like hanging up. I'm sorry. Like, there's some confusion. I guess we were just hanging up.
Okay.
Thanks. Bye.
No problem at all.
Yeah.
Thank you very much, and thank you for attending.
Yeah. Thanks
Bye.
all. Bye.
इसी नंबर पे लगाए थे. इसी नंबर पे लगाए थे.
हाँ वो बहुत लंबा चौड़ा है. एक मिनट मैं दूंगा अभी एक. कौन सी हूँ?
डीएस में
नहीं उससे नहीं होगा. हेलो. हेलो. हेलो.
रिलायंस से.
हाँ हो जाएगा. हेलो. अरे बोल ना. हेलो.
रिलायंस.
हेलो.
वालेकुम अस्सलाम.
ये कोड नंबर इंग्लिश में बात होती है. हाँ.
Your conference is ending now, as requested by the host. Please hang up.